Maria, we're going around the room again. 100,000 pound block is supported by a strut and two cables. Determine the force exerted on the pin at C by the strut and the two cables. Okay, is there anything in the words that's not given in the picture?
The weight of the block.
The weight of the block. So W is equal to 100 pounds, and I'm going to draw it. Oh, sorry, 1,000 pounds. Sam. Okay, what do we need to find? Supported by a strut and two cables. Determine the force exerted on the pin. The pin is right here. By the strut and the cables. So, what do they want us to find? What do they want us to find about the cables?
Tension.
They want us to find tension. So, what do you want to call the tension? You want to call it TA?
Sure.
And then what do you want to call this one? TD maybe? But what do we know TD is going to be equal to? The weight, which is 1,000 pounds. So we already solved that part. But they wanted us to find TA. They wanted us to find TD. So in this case now, I don't remember who asked me. Chelsea, maybe it was Chelsea who asked me. No, it was Jose who asked me, do I always do find at the end? In this case, I'm drawing and writing find at the same time. I just want to make sure that my variables match. So I call this TA, I call this TD. Again, this picture here is just my scrap work. I'm just going to draw stuff on it. What else do they want us to find? Eric? There's one more thing they want us to find. Strut. They want us to find the load in here. What do you want to call that? Want to just call it S for strut?
Or NS, because isn't that the normal force abnormal?
Could be, but the term normal only means it's a contact surface, so it's when something's touching something else. But
Isn't
these
it
guys are connected. The cable's connected in here. So it's, I
Oh,
guess
so
we
it's
could
not
call-
like it's a cable hanging down and then it's pushing
Yeah,
it.
I think, you probably could use an N, but
Or
let's
S.
just call it S.
It does say two cables.
Say it again?
It does say two cables. Strapping two cables. It's not just typing here.
Oh, I see. Thank you. Good. Okay, so let's do our table. Force, magnitude, direction. So Enrique, what forces do we have?
The weight
We have the weight, which we know. What else?
and tension A.
Okay, tension A, do we know its magnitude?
No.
No. Direction?
Yes.
Okay. What else?
Tension D. which-
Tension D, do we know it?
Yes.
Yes. See, everybody, we're checking off TD because we know, we already said it's all transmitted right through here. What else?
And then the S for
Strut. Do we know the magnitude?
No.
Direction?
Not
We know
I
it's
guess-
along here.
Yeah.
Everyone, we know the strut's direction is along here. We don't know if it's a tension force or a compression force yet. We haven't thought about it much. But as long as we know the line of action, it doesn't matter if it's going that way or that way. We know the direction. Lucas, how many unknowns do we have?
Two unknowns,
2 unknowns. How many equations do we
two
need?
equations, one
How many
body.
bodies?
Yeah.
One body.
1 body. What body do you want to analyze?
The pin.
That place at C, right?
Yeah.
Why did you pick that point?
Because all the forces
All the
are.
forces converge. So we draw TA going up. We have a 25-degree angle. And we have the weight going down, which is 1,000 pounds. Okay, so now I want to stop for a minute. We're going to let's look at this picture, the physical picture that's going on. So can you imagine some bracket some strut, BC is here, and there's a cable here and a cable going down. If this bracket wasn't there, what would happen to the weight? It would just slam right against the wall, right? So would you say that that strut is actually pushing the cable away from the wall?
Yes.
So show me the direction that the strut is going, up to the right, wouldn't you say? Because if it wasn't, so it's gotta be pushing on C. So would you call that a tension force or a compression force? Compression, okay. So one, you look at it and you think about physically what the hell is going on, okay? Second, let's look at our free body diagram. TA is going up to the left. W is going down. If we look in the Y direction, is there a balance right here? If the weight's going down, is there something going up to balance it off? Let me say that again.
Yeah.
Looking at the free body diagram we have right now, W is going down. Is there a force present in this free body diagram that could counteract that weight going down? Yes, what? TA. But TA is also going to the left. Is there anything balancing it off to go to the right? No, not yet. But you know we haven't put the strut in, so which way does the strut have to go?
Right.
Up to the right. But we're not going to draw it that way. Okay? So we know by looking at this both physically and balancing forces that S has to go up to the right. But there are many times in statics when the problems get more complicated, you're never going to know which way the force should go. Should it go to the left or right? No idea. Does it go up or down? We have no idea. So we're going to use that no idea right now to see what's going to happen with our answer if we assume the wrong direction. So I'm going to make believe I didn't think about the problem at all, and I'm going to put the S going down. So if we go back to my steps, remember the setup included the given all the way to draw the free body diagram. We finished all the setup now. What do we have left? We have the rest of it to do. We have to find the components of the forces and then use the equilibrium equations. So right now, that's what I'm going to do here. And we're going to use our three-step process for finding everything. So what do we have? The weight of A, we know, is negative 1,000. Oh, we didn't draw an axis. We missed something on the free body diagram, right? So let's draw X and Y. So WA is negative 100 J, and the units are pounds. How about TA? TA is equal to TA, because we don't have the magnitude, times, what is this? Cosine, what's theta x?
115.
115 I plus cosine of 25J, and we know the units are going to be pounds. So TA times, what's cosine of 115?
Negative 0.4226.
X. Plus, what's the cosine of 25?
0.9063.
We could do checks, but we're going to move ahead because you guys have done so many checks that we know we're going to get it completely right.
but in our homework we should.
But in your homework, you should.
Okay.
I mean, I'm not gonna ask you for checks, and if you don't do it, and the problem in the end, and the answer in the end, I mean, I would do checks all along. Because at the end, you don't wanna get a wrong answer. There's really only one thing to check, the unit vector, and the positive and negative too. Okay, so did everybody see? Normally, what we did when we did components is we had a value of the force, but we don't have a value. So the variable is representing the value. So it's TA times, we got this is my unit vector. So this right here is my x component of TA, this is my y component of TA. So let's do the s now. 60 plus 90, right? 180 minus 80, minus 60 is 120. What's the cosine of 150?
.8660.
0.660?
8.866.
Oh, of course. Okay, and 120 is 0.5.
Yeah.
This is an S. Negative 0.8660 S. I. Plus the negative 0.50 S. J. And if ever anybody's finding that, taking all the notes is distracting from learning, somebody could always take this at the end of class. You can keep this, and we can make copies or something. Okay. So we got TA, we got the weight, we have S. So now let's do the equilibrium equations. So sum of the forces in the X equal negative 0.4226 TA, right? Minus 0.8660 S. Equals 0. Sum of the forces in the Y. Zero point 9065 TA.
63.
63?
Mm-hmm.
Thank you. So the weight is a Y value, right? So I added it into the sum of the forces of the Y. Do you see it? So here is the TA value. Here is the S value, and W has no X component. Here's the TA, here's the S, and here's the W.
Should that be a full 1,000 or the unit vector negative J?
Well, I didn't put any J's in because I'm doing some of the forces in the Y, right?
Right.
So I didn't put a J in here, a J in here, or a J in here. What if I said sum of the forces in the Y equals 9063 TA minus 0.5 S equals 1,000? So mathematically, is this correct? Mathematically, it's correct, because that's all I did is I took the 1,000 and put it on the other side. But statics wise, is it okay?
No.
Why not? Because you're saying this, the thing is moving in the Y. Right? Does everybody agree with that? By putting this equation, I'm telling you that it's a dynamics problem and it's not a statics problem and it's moving. This is incorrect. In statics, we always have the sum of the forces equal to 0. Sum of the forces equal to 0. Then, after you write that, if you want, you can say 0.9063 TA minus 0.5 S is equal to 1,000. You could say it then, but notice, what did I not put here? I didn't say sum of the forces. Okay, so turn to the person next to you and just talk about this a little bit and see